Now, till now we have seen about resonance frequency, which is 1 by under root LC, and at this frequency we will get maximum current, right? And this is half power frequency omega 1 and omega 2. And at omega 1 and omega 2 you will get same value of current, that is maximum frequency divided by under root 2. Okay, and the formula for this two frequency omega 1 and omega 2 is, we can use this formula, minus r by 2l plus under root of r by 2l square plus 1 by LC. And similarly the value of omega 2 will be r by 2l plus under root of r by 2l square plus 1 by LC. So we will understand this concept with the help of simulation. So our supply voltage is 100 volt at 50 Hz frequency. This is a series RLC circuit. Resistance is 10 ohm, inductance is 100 millihenry, and capacitance is 1000 microfarad. Okay, so we have resistance, that is 10 ohm, inductance, that is 100 millihenry, and capacitance is 1000 microfarad. The value of XL will be 2 pi FL, and this will give you 2 pi into 50 into 100 milli, right? So this will be 10 to the power minus 3. This will give you 31.4 ohm, and XC will be 1 by 2 pi FC. Just put the value of C and F in this, you will get 3.18 ohm. So the impedance value will become R plus JXL minus XC, and this will give you 10 plus 31.4 minus 3.18. So you will get 28.22. Okay, and if we convert this into its magnitude and angle, we will get 3.33 at an angle of minus 70.49 degree. Okay, so if you want to solve this, you can put that is mod z is equal to under root of 10 square plus 2.88 square. You will get 3.33, and to find angle of z, that is tan inverse of imaginary term by real term. So 2.88, sorry 28 point, this is 28, sorry 28.22 square, and this is 28.22 divided by 10. You will get this value. Now we need to find current and drop. Okay, so to find current, I, that will be equal to V by R, right? Sorry, V by Z. So V is 100 at an angle of 0, and Z is 3.33 at an angle of minus 70 point, let's take 5, okay, 5 degree. This will give you 3.33 at an angle of minus 70.5 degree. Please correct this value to plus. This will be plus 70. Okay, and this will also plus 70. Now in question they asked to find drop, but we don't need this. Okay, see, my main objective is to find the resonant frequency and see what will be the current at resonant frequency and also at half power frequency. Okay, so if you want to find current voltage drop also, that voltage drop across VR will be equal to I into R. So I is 3.33 at an angle of minus 70.5. So multiply this with R 10, you will get 33.3 at an angle of minus 70.5 degree. VL will be I into XL. Okay, so I is 3.33 at an angle of minus 70 degree into XL will be 31.4 at an angle of 90 degree. Okay, because here VL will be leading current by 90 degree, right, in RLC circuit. I into XL will lead current by 90 degree. Okay, so this XL will be 31.4 at an angle of minus 90 degree. This will give you 104.5 at an angle of minus 70 plus 90. So this will give you 19.5. Okay, and similarly Vc will be I into Xc, that is I into 3.33 at an angle of minus, sorry, this will be 3.18 at an angle of Xc. So Vc will be in lagging nature, Vc will be lagging current by 90 degree, right, in series RLC circuit. So you will put minus 90 and this will give you 10.59 at an angle of minus 160 degree, 0.5 degree. Okay, so you can find this values. Now what is our main objective? Our main objective to find the value of current at resonant frequency. Okay, before frequency of the supply was 50 Hz. So how to find resonance frequency? That is 1 by under root LC, right? So this will be under root of 0.1 into 0.001, right? L was 0.1 and C is 1000 micro, so it will be 0.001. This will give you 100, okay, 100 radian per second. Now FR will be 100 divided by 2 pi and this will give you 15.9 Hertz. Okay, let's take the approximate value 16 Hertz. Now omega 1 or 2 will be minus plus R by 2L plus under root of R by 2L whole square plus 1 by LC. Now just put the value of RLC, you will get minus plus R by 12 will give you 50 plus this will be 50 square plus this will be 10,000. So you will get minus plus 50 plus under root of 12,500. Okay, now what will be F1 and 2? Or I write the value it. This will give you 61.8 and omega 2 will be 161.8. Okay, and what will be the value of F1 and F2? So F1 will be 61 by 8 by 2 pi, you will get 9.83 Hertz, and F2 will be 161.8 divided by 2 pi, you will get 25.75 Hertz. And at this frequency our current should be equal to Im by root 2, right? And at this frequency, resonance frequency, your current will be equal to Im. Okay, now we'll put this value under simulation. Now this is our RLC series circuit where R is 10 ohm, L is 100 milli and C is 1000 microfarad. Value of this source is 100 volt and frequency is 50 Hertz. Now if we run this circuit, our current should be equal to 3.33 at an angle of minus 70.75, right? See, yeah. Now you saw the current value is 3.24, which is approximately equal 3.3, and our current is lagging by minus 70 degree. Okay, so let me run this one more time. Okay, okay, so this graph represent your voltage and this graph represent your current. Now you can see here our current is lagging, right? This is 90, this is 180, and our current is lagging. by 70.5 degree, right? This is voltage and this is current. So our current is lagging by minus 70 degree. At resonant frequency, there will be no lagging between current and voltage because what happened at resonance frequency? At resonance frequency, XL will be equal to XR, XC. So current I will be equal to 100 divided by R plus J XL minus XC. So if XL is equal to XC, this will become 0 and this circuit will completely behave as resistive circuit. Okay, so we all know the phasor difference between voltage and current in resistive circuit is 0. Okay, the angle between voltage and current will be equal to 0. So if we put the frequency value at 16 Hz, there will be no phase difference between voltage and current. See, if I change the frequency to 16 Hz and if I run this, see, there is no phase difference between voltage and current, right? Okay. And what we got the value of current here? See, at resonant frequency, our value of current become 9.9. Okay. So let me mention here, at resonant frequency, our current is 9.9 ampere. Okay. So this is nothing but IM, maximum current. Okay, this is maximum current. What will be the current at half power frequency? That should be 9.99 divided by under root 2. Okay. So if we change the value of current, of frequency to half power frequency, that is 9.8. Okay, 9.8. Now you can see the value of current has reached to 7.12. Okay, so we got the value 7.12 and we will get the same current at 25.75. So if we change the frequency to 25.75, and if I run this, you can see that 7.5 Hz, 27.75 Hz, we got 7.24, and at 9.83, if I change this value to 9.83, we will get 7.2. Okay, so let me correct this. 7.2, this is 7.2. Okay, now I'll add this approximate value because this was 7.1 something, right? So this was 7.2 ampere, and let's take this as 10 ampere. Okay, your value will be approximately equal to this value because of the internal resistance of ammeter, so don't worry about it. Now at this frequency you will get the current Im by root 2. Okay, so what is Im here? 10, right? And 10 by root 2 will give you 10 by root 2, that is 7.1 ampere. Okay, so this is approximately equal to this value, right? So if we plot this if we try to plot this at omega r frequency, omega r, so omega r was 100 hertz, and what was the half power frequency? That is 61.8, and omega 2 was 161.8. Okay, so this was our bandwidth, and at omega r we got maximum current. That is 10 ampere, and at omega 2 and omega 1 we got at omega 1 and omega 2 we got 7.2. okay, or take 7.1. all right, so this graph will be like this. Okay, so this is your resonance frequency, and at omega 1 and omega 2 you got the same value of current, right? So I hope this simulation help you to understand this better. In the next video we will see parallel resonance circuit. Thank you.